Hello? Yeah. Oh, yeah, sure.
Hey, I'm here to introduce Mohit Mehra from Children's Hospital Los Angeles. Mohit's a lead data engineer working on solving complex problems in the area of pediatric critical care medicine. His mission is to leverage open source big data technologies to help develop machine learning algorithms that can assist clinicians in making near real-time decisions at the bedside, and also continue collaborating with like-minded researchers who care about our little ones. He'll be presenting a talk titled Big Data in Pediatric Critical Care. Please join me in welcoming Mohit.
All right, thanks. So yeah, my name is Mohit Mehra. I am a data engineer with VPQ, and today I'm going to talk about big data in pediatric critical care. So this is what an intensive care unit looks like, especially it's a pediatric intensive care unit. And as you can see from this picture, there's a whole slew of medical devices, telemetry equipment, imaging devices, and other kinds of breathing tubes, etc., all kind of chaotically sprinkled across this room. But what we really don't see is this little kid whose life is actually dependent on the data that comes out of these devices, and ultimately the humans that are responsible for making decisions based on this data. So it goes without saying, data is super critical for us. And that's precisely the reason why our chairman, Dr. Randall Wetzel, started Viveca, which stands for Virtual Pediatric ICU. And our mission is to assist doctors and clinicians in making accurate decisions based on data. And just in simplistic terms, it's basically trying to find similarities between a patient at the bedside with a historical population with known outcomes. So this is a slide that actually stuck out to me. In fact, one of the other presenters also used this slide. And it shows the current big data landscape. And as you can see, it's like several hundred companies that are now in this space trying to do big data and machine learning. In fact, their use case is all centered around the customer. Customer analytics, customer experience analytics, etc. And I guess the question that we ask is, where is pediatric healthcare? And before we can really answer this question of why critical healthcare is not part of this bubble map, we can just take a quick detour of the history of IoTs in the ICU. And essentially it can be divided into two eras. One would be going from the 40s to the 90s, where you start seeing these very specialized medical devices that are really responsible for monitoring and measuring very specific parts of the human body, such as the heart, of the brain, etc. They come into the ICU without much data sharing. And then in the 90s, you start seeing some network offloading of data, and then government introducing things like HIPAA and Health Level 7, which is a format for streaming data. But not until the mid-2000s we start seeing a larger set of repositories that store hospital-wide data, and that's what an EHR is, which stands for Electronic Health Record. So the story of EHR adoption across the US is a pretty promising one. We start, the government mandated meaningful use in the year 2008, and since then we've just seen a steady growth in hospitals certifying EHRs, which is actually a good thing for us researchers because we rely upon high quality data from EHR. But there remains several challenges that need to be overcome. Number one, interoperability. So the medical device industry, and again, I'm going back and explaining why healthcare and generally critical care is not part of the big data map. So the reason is medical device industry is still using proprietary protocols and formats. There's a big liability component to it. HIPAA's privacy and security regulations, they've just led to a protectionist culture where people who are responsible for hosting this data are not really sharing the data with researchers. So you have to jump through these hoops to get the data unlocked. But really what the big data community is more interested in is the velocity and the volume of data. And it does exist. The devices in the ICU are actually, some of them actually generating over 100 samples per second coming from the heart or the brain and other organs, leading up to like possibly several petabytes of waveforms. But essentially, without proper storage solutions, you essentially see a 72-hour period after which they're getting dropped off. And then last is a very soft one, but it's essentially the healthcare IT has not upgraded their skill set to adopt the big data technologies. And so what we're doing at within the VPQ at the data engineering is we like to look at the companies which this audience is aware of mostly, and that is, all the companies such as Apache. We love open source. We use a whole bunch of Apache code. We use Node. Amazon is our provider for data in the cloud. We use Atlassian for Jira project management, etc. And then in Hadoop, we actually are using Hortonworks for Hadoop. And Hadoop actually now plays a big part in what we do. So our Hadoop journey basically is just a 3-year-old journey, but when we started out evaluating how to create a single large data repository in the hospital, there were a few solutions out there, but we felt that Hadoop was the way to go. So we started out with a Hortonworks HDB 2.2 and Ambari 2.1, which is a very old version now. And then we just through some very basic services. The goal was to try and see if we can ingest as much data from the hospital. And then we just used like HDFS, Hive, Ranger, and Uzi. And then as part of this journey, we kind of learned from the infrastructure side of things, like how do you do upgrades. When you write custom jar files, your data pipelines break. Or what happens when your audit log space runs, when you run out of space. And like I said, it's a 3-node cluster, and then if one of the node goes down, it's a big problem. And then again, since we're again on a grant and a funded, by a grant, we just cannot go and expand to like 200 nodes on-prem cluster. So user group multi-tenancy actually plays a big part in it. You have ingestion process that's writing to your HDFS cluster, but then you also have users that are querying that cluster at the same time, and that can lead to resource contention. So how we dealt with it, we kind of learned from it. And this is kind of our existing on-prem infrastructure, high-level schematic diagram. And we're using, again, Hortonworks Hadoop Stack with HTTP 2.5 and Ambari 2.2. And we have actually moved from a 3-node to an 8-node cluster. Ooh. And so it's still, the reason why I say ooh, because if you look at Yahoo, I attended a Yahoo presentation, and they said, yeah, we just have 2,000 nodes. It's like, okay. So, but it's really important to understand that we have a Hadoop cluster that actually is helping us build our infrastructure. So what kind of data sources are we talking about? So we typically have 2 kinds of data sources, batch and streaming data. And when it comes to batch data sources, it's actually broken down into several smaller databases, even larger databases, such as the EHR data that gives us all the human charted data. We have Philips monitor data that actually gives us all the vitals that are hooked up to the patient. And so we read a lot of that data from there. Also, labs gives us things like blood gases and all the blood work that gets done in the hospital. Medications data actually gives us a good understanding of what medications were applied to a patient and how did they do with those medications. And then again, there's very specialized intubation and ventilation data sets, which essentially give us an understanding of whether the patient was on a respirator and whether they were intubated or ventilated, and what were the circumstances under which they had to be intubated. Then we also have streaming data sources, which are basically coming directly from the ICU monitors. We use HL7, which is, again, health level 7 for those who don't understand or have a background in healthcare. And this is just a special format in which streaming data is made possible. And again, we are getting things from the monitors. We're getting ADT, which gives us admit, discharge, and transfer of the data, whether the patient was, what time the patient was admitted into the ICU and what time they left. So there's a lot of that kind of data that we are receiving from there. Once the data actually, so that's the static and the streaming data sources. We also use Uzi for our ingestion process. So we run hourly, daily, or weekly. These different jobs are running at different times of the day. Scoop is something that we have really heavily used because it allows us to easily go and fetch RDBMS sources. And then again, we have written our own jars for some REST APIs that allow us to pull more data in. So we're very data hungry because that's what our data scientists love. We just want to get more data. But ultimately, these ETL jobs, they actually push the data into HDFS. And from there, we could basically create Hive tables. And our goal has always been to retain as much raw data as possible because we don't want to make any transformations or mappings on the data. And then the other side is how do we handle streaming data? We use very special, again, this is a very special healthcare engine that allows us to transform HL7 into JSON. And it can handle, it has queuing capabilities that can actually handle frequencies of like about 15 seconds to 4 hours. So that's basically handling the HL7 streaming in. We first tried to put all the streaming data into HBase directly, but then we found there were some reliability concerns and issues. We started losing some data, so then we added NiFi and Kafka on top of that. All right, so what happens when the data actually makes its way into our cluster? Well, one of the use cases is for the analysts and even the physicians themselves who can really understand some of the dashboards to go and create their own dashboard. So this is an example of one of the doctors asking us, create a dashboard for us that they can see all the patients in the year 2015 with a primary diagnosis of scoliosis. And they wanted to break the data down into how much time did the patient stay in the encounter, bucketed by their age group, and then maybe color-coded by gender. So this is just a Tableau BI tool set that we're using. Another note about Tableau is that it's really not a very good big data live connected software. So we have to offload a bunch of data set into Tableau's server in order to get the performance up. And then Spark, I mean, that's obviously it's a great tool. Everybody kind of knows Spark here by now, but it's really helped us a lot with creating data pipelines. And why do we need this data pipelines? Ultimately, what we want to do is, once we have the raw data, we want to convert that into a machine learning data set. So the Spark allows us to do data cleansing, things like null values, what do you do with those? Data tagging or munging, which allows us things like if you have a date of birth coming in, then can we tag age at admission? Or even a little bit more sophisticated things like calculating z-scores for each observational value that shows us how deviant a value is from the mean. So things like that are really easy now in Spark, and we're able to do that. And then of course it helps us with de-identifying the data because our machine learning data set has no patient information in it. And then with Spark, we found Zeppelin to be a really useful tool because again, it allows us to write SQL, Python, and Scala, all three of these languages in one notebook. I've done that even on one pipeline, which is crazy, but it helps. Zeppelin can easily connect to Spark or other data sources, and we found that helpful. One of the other things about Zeppelin we found was that it is actually lacking, its plotting libraries are not as great. So we, in fact, it allows us to import specialized Python libraries like matplotlib and other libraries that do a little bit more advanced plotting. All right, so once the data is munched and aggregated, what does it look like to as a machine learning data set? Well, I could not really present that because it's crazy amount of data and it's pretty complex. But this is kind of an overview of like what the data looks like. So what we try to do is we create a time series of, it's a kind of a sparse matrix that is on a time interval. We just basically stack categories of variables on top of each other. So there could be several observations, including vitals and labs and drugs, even the medications within a time period. So like, within, let's say, 1 hour, let's just stack all of them together in one, on top of each other. So that's kind of how the machine learning data set feels like. And I can talk more about the complexities behind the data itself, and hopefully if I have time, then I can do that. So once the data is now moved, now we're moving from left to right, and our ultimate aim is to present the data to data scientists. And we want to eliminate any kind of redundant work that they are doing over and over again with the data. And that is why we try to do all of that work in Spark. So at the moment, we are working with NVIDIA GPUs. And one of the algorithms that we feel strongest about in making accurate predictions is the recurrent neural network. We use LSTM for that, and we train our models using this algorithm. In the past, we have obviously worked with a whole bunch of other algorithms like logistic regression and NLP and etc. But this neural nets is actually, we feel, is the way to go as far as medical data is concerned. And then Keras is one of the frameworks for machine learning that we're using. Someone like myself who was not a data scientist can also use that. So we've been playing around with that framework. One more thing that I don't have an arrow for, but it's at the bottom. We actually have, once the streaming data makes its way into HBase, we have Express.js and React.js for our app that we're using. We have built a bunch of applications and APIs on top of the HBase data store. So that's kind of where the apps are at the moment. All right, so one of the challenges with on-prem infrastructure is truly scalability. You cannot really scale when you have a hospital that's hosting your data content and maybe USC. For us, it's actually USC data center. So what we want to do is try and see how we can go to the cloud. Now, one of the biggest challenge of going to the cloud is what's called PHI, which is personal health information. And you cannot just take all the patient's data and put it in the cloud and later on find in the news that some, I'm going to use the word Russian hacker got to it. So what we do is we actually do a very diligent job of stripping all the PHI. We actually have written tools that anonymize the data, and then once the data is completely anonymized and has gone through a thorough review at the hospital, we're allowed to take that data and push it up into the cloud, where we have so many possibilities. It's so easy now with the cloud to at least infrastructure-wise, setting up the infrastructure is a lot easier. So then in this case, yeah, we just use a private VPN and push it up to a bunch of S3 buckets. And again, here we are using Hortonworks HD Cloud. It's like a new tool they have, which is basically spinning up Spark nodes on demand. So it's just easier. Again, trying to keep cost to a manageable amount, and we just shut the cluster down once the training is done and the pipelines are all executed. But then again, the ultimate goal here is to take the data and then send it over to our GPU cluster, which we're using Amazon P2 for. All right, so that brings me to how much data is really enough. Now, this is actually an important slide for me because it gives us the assurance that more data is better for us. And this is an example of ROC AUC curves, which are predicting one thing, that's one context, early warning system. It's called patient early warning system performance. And we used RNN to train on it. But what you can see here is that with just 10% data, we have about 70% accuracy. And the accuracy now starts going up as we add more data to the training set. So that's kind of one of our hooks to try and get more data from the hospital and make sure that they understand how critical data is for us. All right, so I guess this is a short slide, but I guess in a nutshell, what we're trying to do is we want to save lives, and we feel that saving lives depends upon making timely and accurate predictions. And then more data and better algorithms are definitely something that we are always working on. And then ultimately, the big data technologies here that we see all over, they're going to help us with enabling our research and development. And then, yeah. So this is just when I talk about research. This is our research. We have a whole, slew of doctors who are very passionate about children's health, and in fact, some of them can write code. And so go figure, after 8-10 years of medical school, they can write Python code. And then, we have some research scientists and data scientists working across with us. One of our proud moments was actually working with JPL on actually something similar to what they are doing in clustering, and hope that we can apply that technology and use it at children's hospitals. All right, so that's it, and I'll take any questions. Yes?
Just curious how you look at time series data and anomalies and normalizing that between your various sources. How do you go about dealing with that as a problem for you?
Yeah. So medical data is very complex. It's not like a Twitter host feed that you're getting and it's coming from so many different sources, and trying to stack data on a time series is a pretty big challenge. And what we try to do is, as I mentioned, we ultimately envision the data as a irregularly sparse matrix populated as that. And then we can continue our research with that. Now, just exactly how we transform the data within a deep learning pipeline, I'm not the right person to talk about that, because our data scientists can even go further than and tell you that. But from a data engineering point of view, yes, it's a big challenge for us. Yeah.
Are you presenting the predictions to doctors today to help them with the decisions?
Yes. So we constantly work with the doctors, and these are Children's Hospital is a learning institution. So we have Keck School of Medicine, which is USC's Keck School of Medicine. So we keep getting residents, and we're always working with them to kind of project what our results are. And I think one of the keys to that is like we feel that especially the young residents, they don't have enough training. And I mean, if all you could remember from this slide, you should just, this slideshow is just one slide, and that's that ICU, right? So in that ICU, it's overwhelming, not just for the parents or the families, but even for doctors. When they come in there, they're getting bombarded with just information all over. So that's our hope, that we want to assist them. And again, it's for us, it's more of statistics. We want to be able to slice and dice the data, and then we have created some sub-contexts. So an example is like, how do we predict mortality, or can you predict diagnosis for the patient, or whether specific treatment will have any physiologic trajectory that will change. So like a medication causing a higher heart rate or a lower BP. So all those things we'd like to predict, and again, it's all in terms of probabilities. So that's the way we like to communicate to the doctors. And I can't say how much of it is like really being used at the moment, but I think there's a lot of potential. And as I mentioned earlier, it was also because of our data was not enough. Like, when a physician is looking at a patient, they're not just looking at the data, they're also looking at the patient. Now, whether a patient is paid or not, was that actually captured in the data? Maybe not. So some of the doctors who are seniors, they can actually look at the patient and go, oh yeah, I think this is wrong with him, and this is the treatment. So we want to get to that stage. That's our goal. Yes?
So can you tell more about, so do you have any machine learning based systems that are actually used by the physician and are influencing their decisions, or, or they're still like looking at them with skepticism?
So, not in a live setting, but as a retrospective research, yes. And I think our goal as data engineering team is to say, well, you got some models that you built, and these doctors are really liking what the predictions are. Let's bring it back into a streaming data, and we would like to predict that. We haven't reached that yet, but that's our goal.
So, for example, there was a slide about an early warning system. Is that something in production, or?
Oh yes, that early warning system. Think of it as it's kind of a linear. It used to be thought of as a linear problem, more so as now we treat everything as a non-linear problem. So there's already several scoring systems out there. Pew's system, which is what that is, but there's other scoring system which tell the physicians of a state of a patient. And they were more linearly calculated. But I think what everybody's realizing, it's not as linear as just that. So we're working on that.
Just a quick one. Great presentation, by the way.
Thank you.
At lunch, you say something about, you guys anonymize the data sets, right, before you push it to the cloud, right?
Yeah.
I believe at some point too, right, you query the data, those data sets back, right? How's it like? Is it challenging, going back to, it's just almost like you have to place those names back, right?
Not necessarily, because think of you as a doctor, and you have gone through years and years of training, you've seen several cases. It's all in your head.
Yeah.
When you see a patient, you don't remember which patient had what. You only remember a cluster of patients. So we don't, at this time, we don't want to tie the real patient to the historical population. But as long as we're able to predict similarities in data, we've actually achieved our goal.
How do you handle the unstructured data that is sitting in the EMR as progress notes, lab reports, which is, do you do that in NLP?
Yeah, so that's a good question. NLP is a hard problem for especially medical community. We, think about this way, these guys go to medical school for like a decade almost. And they come out and they start speaking this language, which is all in the journals. And now, no two doctors even speak the same language, right? So NLP is hard for us. A great example I can think of is we get an observation that says MAP, which is map. What does it mean? Well, one doctor says it means mean arterial pressure, and the other guy goes mean airway pressure, right? And they're completely different things. One is measuring the heart, the other is the respiratory system. So NLP is a challenge. We are trying to do some of the more traditional computer science NLP problems like the Levenstein distance and things like that, fuzzy logic that allows us to see how close these variables that we're getting to a standard and normalized data set.
Thanks.
Yeah.
How many hours of data do you need before you can start making somewhat accurate predictions on patients?
Yeah, good question. So one of the challenges that our doctor put in front of us is that by just looking at the first 6 hours of encounter data, can you actually predict what the last 6 hours will be like? So that's one of the challenges we want to obviously at some point be able to answer, but there's no simple answer for it. Some of them could be as simple as very little data that can give you a lot more. But typically the kids that come in ICU, they're pretty complicated cases. So a lot more data is needed.
So a lot of healthcare data is very time sensitive, and it's only meaningful if it's being captured in real time. And one
Yes.
What, for, like culturally, I mean, how do you support clinicians to chart in real time?
So can you rephrase your question? I guess, sorry, I don't want to answer something wrong.
So I can explain my problem that I had, because I work in the quality department for a hospital, and we do a lot of retroactive review. And a lot of the charts fall out or fail because basically people are not charting in time.
Yeah.
So, that data becomes useless because it's not accurate. So
Yeah.
how do you support your clinicians or encourage them to do that?
So EHR is our big source of historical data analysis, an electronic health record, which basically shows us over a longer period of time, let's say a decade, how the data was captured and what was stored. That's the first source that we look at. But lately, we have also started looking at real-time monitor data. But again, these are number of variables that are coming out from a monitor data set is far less than what you would need to make an overall decision. So even though we're working with almost 200 variables, almost think of it 200 dimensions, we still feel that the real-time data is not getting captured enough to a point where it can answer everything. Yeah. So that's definitely a problem. I mean, and the picture itself speaks for it. It's an old picture, a pretty old picture, the ICU picture, but that's still the case. It still looks like that. Yes. Is that last question?
Maybe political, but I mean, your anonymized data. Is there any work going on to publish that? I mean, there's other things like Watson and other sources.
Yeah.
I mean, it seems like there are islands of data out there that could be brought together. Is there any efforts to do anything like that?
Not that I know of at the moment. We first want to just work with hospitals. So like we want to collaborate with Stanford, let's say Medical or some other, and then we share the data with them. Getting the data sets to a point where it's universally publishable, it is, like you said, it's the only thing that hinders is politics and bureaucracy in there. Like, at some point, the community has to decide that, what, we're talking about kids, and we're talking about saving lives. So if those data sets can be shared by more people and we download it, then that's going to be the case. But not at the moment. At the moment, we are we're working on open sourcing our anonymization code. That's it. Okay. Thank you very much. Appreciate it.